All right, we're going to be going over 5-7 complex fractions. I'm going to do a few of these problems. I'm going to do number 1 and 3 to show the two different methods that you can do. The first method is to simplify the numerator, simplify the denominator, and then perform fraction division to combine those two things together. I'll do that on the first one. The second method is to find an LCD, a lowest common denominator for all of your fractions, multiply the top and bottom by that LCD so that you get rid of the fractions that are on top and the fractions that are on bottom, and you just have a single fraction left over. All right, first one, simplify the top, simplify the bottom, put it together. All right, so our top is 3/2 minus 1, which is 1/1. Well, we need to make a common denominator here. It's pretty easy. We can make a common denominator of 2. So 1/1 can really just be written as 2/2. Cross that out. So 3/2 minus 2/2 gives us the top to be 1/2, a half. The bottom, slightly harder, but not too bad. We have 5/6 minus 2/3. All right, well, common denominator here would be 6. So I can turn this one into 6 by multiplying by 2. So that becomes 4/6. All right, so we're doing 5/6 minus 4/6 should give us 1/6. So this is what our complex fractions become. A little bit simpler than it was before. Now, the way that I can think about this complex fraction as this fraction divided by this fraction, or written this way, 1/2 divided by 1/6. Well, when you divide fractions, you're supposed to change this to multiplication by the reciprocal. So it's going to be 1/2 times 6/1. Multiply that. 1 times 6 is 6. 2 times 1 is 2. 6/2, which actually is just 3. So that whole complex fraction up there is equivalent to a whole number, which is equal to 3. So this method works pretty well with numerical fractions, because you can add and subtract fractions pretty easy and then just use fraction division to finish it off. Okay, next method we have is we're going to find an LCD, or actually a lowest common multiple of all of these denominators. So we have 2, 5, 6, 8. This is kind of the hardest part. We need to find a least common multiple for all of these numbers. So it's easy enough to do them kind of pair by pair, I guess I would say. I know that 2 and 5 have a lowest common multiple of 10. That one's pretty easy to figure out. 6 and 8, that's a little bit harder, but 6, 12, or let's start with 8. So 8, 16, 24, 24. 24 is a multiple of 6. And then I kind of get in here between 10 and 24. Maybe I'll list multiples of 24 until I have something in common. So 24, 48, 72, 96, 120. 120 is a multiple of 10. So there we go. I have figured out my LCM or LCD for this fraction. It's going to be really important. It's a very important number for us. I'm going to be multiplying the top and the bottom by 120. That does not change the value of the fraction because I'm multiplying the top and the bottom by the same things. The fraction, this complex fraction, is still not changing the value of it at all. All right, distribute this in. Half of 120, it's going to be 60. 1/5 of 120, so if we divide it by 5, that's going to be 24. 1/6 of 120, so that's going to be 20. And then 1/8 of 120. So that's 63rd 15. Some of these things are a little bit tricky to do. This part right here, finding the LCM, LCD, it's helpful to find the lowest one. You can get away with just finding a common one, but finding the lowest helps later on when we go to simplify this. But you know, this is kind of where a lot of our work is. This part and then multiplying it in. But now you can see it's fairly simple to now simplify this. So 60 plus 24 is 84. And 20 plus 15 is 35. Now, you would want to go ahead and look and see if these can simplify. And actually, in this case, they can. Both of these should be divisible by 7. So 84 divided by 7 is 12. And 35 divided by 7 is 5. There we go. It's equivalent to 12 over 5. Both methods have their merits. This one seems the trickiest to people when we're dealing with just regular fractions. Seems like it might just be easier to just do a little fraction addition and multiple and then change it to a division problem. But I think this method works a lot better and is really the only method when we're dealing with polynomial expressions as the denominator. So we'll see how we go with the next couple examples. All right. All right, so now we have this example here with some variables. We kind of got rid of the numbers almost altogether. So we have s plus s over t. So really that's s over 1, right? And then this one's really 1 over 1. We can kind of see that between all of our denominators, we have 1 and t, 1 and t. So 1 and t, right? Our lowest common denominator here is just going to be t. So if we multiply everything by t, that should simplify things out quite a bit. So let's go ahead and do that. So multiply this by t, we get st plus. When I multiply this by t, it's going to cancel out. It's just going to leave me with just s. S's look like 5s. I'm not a big fan of that as a variable. Okay. Then here we're multiplying t times 1, just t. And then t times t. These t's will cancel out when I distribute here, so they're just plus 1. Then, to make things even nicer, you want to see if there's any way you could try to factor this and simplify this out at all. And kind of turns out there is, actually. I notice here I have s as a common factor. So this top can factor as s times t plus 1. And then on the bottom, I have t plus 1. Same factor on the bottom and the top. They can go away. So overall, I end up with just s. This extra step here is important to simplify it as much as you can, but really this was kind of, I don't know, kind of like most of the way there without seeing that extra factoring. All right, let's try this again on number 13. All right, on number 13, we're using exponents to stand in the place of fractions. Remember, negative exponents really mean it's 1 over that to a positive power. So I'm going to kind of quickly rewrite this as 1 over y plus 1 over x to the first power. I don't usually write a first power, so there. And this one's going to be 1 over y squared minus 1 over x squared. Okay. So I have a bunch of denominators. I have x, I have y, I have x squared, I have y squared. So if I'm looking for an LCD between these two things, well, I need x squared and I need y squared. That's going to be my LCD between these. Right. because x is a factor of that, y is a factor of that, x squared is a factor of that, y squared is a factor of that. So that's going to be my LCD. I'm going to multiply the top and the bottom by that. And I'm going to kind of show this process a little more. So when I do that, I get x squared y squared over y plus x squared y squared over x. That's on the top. On the bottom here, we're going to get x squared y squared over y squared, x squared y squared over x squared. We can do a little bit of simplifying. On the bottom, it's pretty obvious. These y squareds can go away. These x squareds can go away. So that's going to leave us with, on the bottom here, just x squared minus y squared. And then on the top, not quite as obvious, but this y is going to cancel out with one of these, so leaving 1. And this x is going to cancel out with one of these x's, so leaving just x. So that's going to be x squared y plus xy squared. All right, we are close. This has kind of gotten rid of the complex part of this complex fraction. We don't have fractions within fractions anymore. But there's some factoring that can be done to fully simplify this to its full potential. So on the top, I have some common factors in between each of these terms. They each have an x and a y. So I can factor out an x and a y. That's going to leave a single x here, right? Single x, plus factor out an x and a y. That leaves one of these y's and a y. And then on the bottom, this is really difference of squares. We have x squared minus y squared. So difference of squares always factors as this particular pattern, as conjugates. And now you notice, oh, x plus y, those are a common factor there. They can cancel out. And we should have a final simplified answer of xy over x minus y. A lot of kind of advanced algebra techniques to end up with this final answer.